some of the nitty-gritty of regression. And we're talking about linear regression here. The best way to begin a linear regression analysis is to see variables. And in simple linear regression, we are seeing or visualizing two variables. In the particular example that we have been looking at in the retail problem space, these variables could be advertising expenditure on the x-axis and sales on the y-axis. You can think of these variables, the numbers that you see on these axes, in a unit of choice. You can think of it in, say, thousands of dollars. You can also think of sales as, say, unit number of units sold. But you can, of course, translate that into any dimension or any measurement scale that suits your business. Why am I plotting advertising on the x-axis and sales on the y-axis? Because my purpose is to predict sales or to understand sales in terms of advertising. Sales is my business variable. It is my outcome. It is my output. In statistical terms, we call it a response variable. It is responding to something. These variables, the output variables, the response variable, the outcome variable is on the y-axis. The input variable, the predictor variable, the variable that is influencing the outcome is on the x-axis. Please remember this. You can always visualize it the other way around. But if you visualize it the other way around, you're heading towards a problem where sales is predicting or modeling advertising, which makes sense in its own way, but that is not the problem we're solving now. So, the response variable is on the y-axis. The predictor variable is on the x-axis. Now, let's take a look at this plot. What is in this plot? This plot has a number of points. Each point represents a particular situation. For example, the point near the top could be representing a situation of an advertising expenditure around 400 and sales of somewhere between 30,000 and 35,000. That is a point. What might the point represent? We're not going to go into the details, but the point could represent a particular region. The point could represent a particular point in time, let's say a week. A point could represent a particular channel, a particular retailer that we're using. It could represent a business unit. Any way in which I am slicing or dicing my advertising and sales. Just to fix attention, we might be able to argue that a point here, let's say, represents a particular region. In that region, I now know what my advertising expenditure is, that is visible to the people in that region, and what sales I've accomplished for my product. These are data points that I have. All these data points are now plotted on this graph. What occurs to you when you see this graph? What occurs to you first is that there seems to be a relationship. It seems to be the fact that if advertising increases, sales increases. But it is not a mathematical fact. And this is important. I can look at points. So for example, I can say, look at a point here, which I'm circling now, and a point on the right, which I'm circling here, where advertising expenditure increases, but sales is decreasing. So this is not a mathematical relationship. I can find points here in which the relationship goes in the opposite direction. If this was mathematically a straight line or mathematically the case that as I increase advertising in lockstep sales increases, then I'd have a very simple problem. But as we all know, businesses don't work that way. People don't buy that way. And advertising doesn't impact people in that way. What do I mean by that way? In that deterministic mathematical way. There's randomness in behavior. There's randomness in the effectiveness of advertising. There's randomness in the procurement characteristics of people. So this is not a mathematically true relationship. So if I want to ask what happens to sales as advertising expenditure increases, I will get a rough answer like, on the average, sales is going to increase, but that's about it. I cannot prove it for a fact that if advertising increases, sales will increase. There are many points on this graph that tell me that that is not true. But it is true that in a broad sense, in a statistical sense, in an average sense, more advertising is likely to lead to more sales. And that is enough for me to be able to get at a business strategy. One of the things we promised we would talk about is evaluating how good this is. Is this relationship actually good? Is it close to mathematical truism or truth? Or is it still just almost a random cloud of data and we are forcing a relationship between them? Where in this spectrum of certainty into uncertainty do we lie? We're going to have to take a look at that more closely. But for now, let's proceed with this understanding that we are looking for this relationship and leveraging this fact that there is something relating sales to advertising. This relationship at this point we can say is increasing, or shall we say positive. I use the word positive very deliberately. We'll see what exactly is positive here. But there's a positive relationship. Positive relationship refers to the fact that as advertising goes up, sales goes up. Similarly, as advertising goes down, sales goes down. So they're moving in the same direction. For now, that is what a positive relationship is. Now, not all relationships are positive. For example, what happens when price goes up? By price, I mean an individual product's price. So if the customer goes into the shop and sees a higher price, what will happen? Economists tell us that there could be an income effect and a substitution effect, and many such things will happen, but the net result is that the customer will probably not buy the product. What that means is that if there are a large number of customers, each of whom is now seeing a higher price, on a total scale, there will be fewer sales made. So now if I'm again looking at each of these points as representing the total sales made in a region, if the price set in that region or in the stores in that region is at a certain value, let's say in a particular store, 750, and this is my point, then I'd expect to sell a little over 24,000 units. Similarly, this is not a mathematical relationship, but it is still capturing a basic pattern, and that pattern helps answer the question, what happens to sales as product price increases? And here, by looking at the graph, again, you say, I don't really know for a fact what will happen, but I see a trend, I see a pattern in the data. And that pattern tells me that as price goes up, sales on the average or by and large will tend to go down. And these words like average and by and large need to be made a little more precise. Such a thing is called a negative relationship. The two variables are moving in opposite direction. I can also argue from this that if product price goes down, then sales would go up, indicating that price may be a key driver for sales. And if I want to increase sales, moving price down is likely again to get me higher sales. These are the relationships that we want to take advantage of to quantify and to build greater precision around. It could be that there is no relationship. It could be that we are looking for something that says, are people more likely to buy a product if it is simply described? If I can just describe something very, very simply, are people more likely to buy it? If I can describe a shoe as just do it, is that likely to increase sales? So that's an interesting variable to look at. Why? Number one, the length of a product description is within my control. It's something I can vary. So if there is a relationship, I can take advantage of that relationship and now see whether sales will go up or not. Similarly, in a predictive capacity, I could be able to say that, okay, why am I not selling this? Because length of product description. And if I say reduce the length of the product description, I may get more sales. But the data in this case doesn't seem to say that. Because remember, shorter product descriptions may make the product very snappy, make it attractive, easier to catch the eye. A jingle may help. But a longer product description will also give the customer more information. They can make a more informed decision. And information is quite often power in the hands of a potential customer. And so we don't know which of these patterns is going to win. And when there are multiple patterns like this, multiple market dynamics going on, we don't know what the overall relationship will be. And we end up with a relationship in the data that is neither positive nor negative, but flat. Please be careful. No relationship of this kind may not mean that the two variables are unrelated. It may mean that there are complicated relationships at play, or multiple relationships within the same thing, one having a positive characteristic, one having a negative characteristic. And maybe further analysis is needed with more variables in the picture. That we shall see is a motivation for multiple linear relationship. But for now, there are positive relationships, negative relationships, and no relationships. And we need a way to capture these circumstances. So, when we have these relationships and we have sort of, shall we say, visualized them, can we go a little deeper in characterizing the nature of the positive relationships or the negative relationships, as the case may be? Let's look at these two graphics. Let's look at the left graph and the right graph here. And let's think a little bit as to what the difference is between the two of them. They both have a positive relationship, but there's something that says I should have more confidence in the situation of sales related to advertising on the left than on the right. The right seems closer to the no relationship situation. So in other words, therefore, just saying positive is not enough. I need to have a gradation scale here, a way to understand the extent of positivity, shall we say. The same thing could be true in a negative relationship. We might have a plot that says, really, when I increase prices, most of the time sales does indeed go down. Not always, but quite often than not. But for the plot on the right, that's not really as true. And I see a closer to a no relationship plot here. In these cases, whatever be the nature of positive relationship, it's suggesting the idea that we need to dig a little deeper to understand how positive the relationship is, how negative the relationship is, and get more numbers around this. Put another way, we need a measure of the strength of the relationship. Is it a strong relationship between sales and advertising, between Y and X? Or is it a weak relationship between Y and X? And how do we therefore measure the strength of the relationship between variables? The easy way to do that is to get a single measure of what the relationship is. Why do I say easy? Because I don't need to model the relationship of Y on X. I don't need to get an equation in order to understand whether the relationship is strong or weak. I can simply look at the variables directly and not worry about whether there is some kind of straight line going through the data or not. So let's begin with that. It's an easier problem to solve. What's our purpose? Our purpose is to get a quantitative measure of a relationship between variables. What must this measure do? It must measure the direction of the relationship, positive or negative, and the strength of the relationship, strong or weak. And the measure that we will get towards is a measure called correlation. the correlation between variables. We're going to give a formula for it, but just keep in mind what the correlation is supposed to be doing. Positive, negative, strong, weak. Correlation is a statistical measure that describes the strength and direction of a relationship between two variables. Here we come to a word that inspires fear in the hearts of many. Statistical measures, but worry not. All it means in this case is that the relationship is not strictly mathematical. It is not that if one increases, the other has to increase. It means that sometimes it increases and sometimes it decreases. That is the statistical part of it. You can think of statistics in some way as a synonym of, shall we say, measuring randomness. There's a random behavior between my variables. And the randomness is captured by a statistical measure, not a mathematical number, not a mathematical relationship between x and y, but a statistical relationship between x and y that is influenced by randomness, by chance, by a scatter of points as opposed to straight lines or equations. So the correlation measures indicate the degree to which two variables tend to change together, quantifying both direction and strength of the relationships. We will do this with one number. Now this number, therefore, has to reflect the way we are thinking about this. And actually we've thought about this backwards. I've described certain things as positive and negative, and I've done it a little cleverly. I've done it to reflect what correlations actually do. And correlations, these measures, are between -1 and 1. And as you can see, they can be negative and they can be positive. But they're going to be between -1 and 1 so that I'll be able to interpret the numbers very well. But you can already see that the correlation can be positive or negative. And this should match our notion of positive and negative that's already explained. So a perfect negative correlation, which is -1, the most negative it can be, remember it can't cross -1. One variable decreases as the other increases. And at this point, -1, this is actually a mathematical relationship. If one increases, the other will decrease. This is a perfect negative correlation, a mathematically negative correlation. On the other side, you have a perfect positive correlation. If one increases, the other will increase. These two extremes are in fact not statistical. They are mathematical. They are deterministic. They are not random. One variable directly tells you whether the other will increase or decrease together. Most situations are not like this. If in business you see a correlation of +1 or -1, begin to worry. Am I actually seeing a business relationship, or am I seeing a formula, some kind of accounting formula at work, or some kind of measurement relationship at work, and not really observations that have business variability in them? In the middle lies this no relationship data cloud. Variables are independent of each other. As one increases, you can say nothing about the other variable. The data points are all over the place. You increase one, the other may increase, decrease, sometimes increase, half the time increase, half the time decrease. I don't know. This is where the statistical nature of the relationship is at its highest. Everything seems to be moving randomly and with no relationship to each other. Variables seem to be moving randomly with no relationships to each other. Sophisticated way of saying it is that the variables are independent of each other.